for the introduction and for inviting me to this webinar. So, hello everybody on my webinar on multi-robot coordination. So this webinar is about how to act multiple agents, robots as a team. What we've seen recently is that there's a strong increase in multi-robot systems. So these multi-robots are deployed to solve tasks, to achieve missions, or even to perform better than single robot systems. So there are various advantages of multi-robot systems as compared to single robot systems. However, there also comes some challenges. And one particular challenge is on how to coordinate the individual agent such that mission can be achieved or mission can be improved as compared to single robot systems. So when it comes to multi-robot systems and the team behavior of multiple robots, coordination of actions in space and time is a fundamental topic. So, but what do we really mean when we talk about coordination of robots? So when we look into some detail, we can identify some key tasks, some key coordination tasks in a multi-robot environment. So the first task is sharing or distributing of knowledge. Sharing knowledge is a fundamental task in order to achieve coordination and to achieve team behavior. Another important task is decision making, because robots eventually make decisions, they plan, they make decisions, and the individual decisions they make have or may have consequences to their peers. So coordination of this decision-making process is another key task. And the third task, which is also some kind of related to decision-making and knowledge sharing, is resource allocation. Because in some systems we may have resources available that we can allocate to different robotic entities. So that these entities are fundamental for the specific tasks of the robots. And when we talk about coordination, this resource allocation is this third entity. So without going into too much detail about these tasks, but I'd like to make some kind of observation at the beginning of my talk. First and foremost, I think it's quite natural and very important that coordination is a very complex, or is typically a very complex problem, because the design space for making our decisions is huge. And I give a few examples of this design space. So the first domain in this design space concerns about the various constraints that may be available in the multi-robot systems. So we may have limited energy of robots, and they have to deal with these limitations. Communication bandwidth, communication delay, and also communication opportunities may be limited. So this is another important aspect. Then typically we expect deadlines to be achieved for specific tasks. So these deadlines pose the third aspect of constraints, and there are many others. For example, even some physical constraints like the maximum payload a specific robot can carry and interact with. The second dimension is about the objectives. Typically, in many robotic systems, we may face multiple objectives. The first objective, obviously, is related to achieving the mission. However, we can also typically measure some kind of the quality of the performance of this mission achievement, and we want to increase that. So we want to either lower the completion time, increase some quality of service, or make the mission achievement more resource efficient than others. And then a third dimension of this problem domain relates to the realizations. we can implement coordination achievement or coordination problems either online, offline, and centralized, or in a distributed fashion. There are various ways on how we can realize that. Right? But what is important that these coordination problems, they are highly relevant for many multi-robot system applications, and there's a wide variety of applications out there, ranging from entertainment with multiple robots or multiple drones, monitoring and inspection tasks are very popular and widely used application domain, search and rescue, transportation, and so on and so forth. So that should give you some kind of a motivation why coordination is so important in multi-robot systems. I'd like to make this a little bit more explicit by showing you two examples of team behavior. So the first example on the top, what you see here is a multi-drone constellation change application. So here the main idea is that multiple agents should identify paths from a starting constellation to an end constellation. And then the drone should fly from start to end without collisions. And they should do this as fast as possible or as energy efficient as possible. This can be typically framed in an offline coordination you plan up front, and then in a static environment you can let the drones fly. The second example on the bottom is about swarming and synchronization. So what this example is about is that from simple rules and simple interaction of the agents, one can observe collective behavior, emerging collective behavior. And this has been implemented from self-organization principles, where movement, actions, and phase synchronization is modeled in a unified model, a so-called swarmulator. And this coordination is must be implemented in an online coordination. So where this exchange of information and also the motion planning is done online. Okay, so these are two examples. Now let's briefly talk about some basics to start with. When you look at autonomous agents, the operation of autonomous agent is typically modeled in this sense, process, act cycle. So where sensor data is sensed from the environment, they are analyzed, processed, some knowledge is maintained in the database, reasoning takes place, and then the appropriate actions are issued. So we see this sense, process, act cycle, we see this maintaining and building of knowledge, and typically this cycle are executed at multiple levels depending on the complexity of the tasks. When it comes to a multi-robot environment, we need to expand this key architecture by three basic building blocks. So the first building block is communication, which is responsible for the optimized data distribution of what data should be communicated to whom in what point of time. The fundamental for this communication is connectivity. Right? So in order to distribute and share this data, the agents need to be connected. And typically in many robotic applications, we investigate or be interested in wireless communication, and we want to transfer data with some specific quality of service level. We want to maintain connectivity for the whole period of time, or we want at least to guarantee some intermittent connectivity with some time constraint. And then on top, we perform this coordination where we decide on our decision makings on the multiple agents. A different view on coordination is adopted from this survey, which has been published a few years ago, where the ASIs looked at the design flow of cooperation. So what you typically see is you start with complex tasks that the team of agents should solve and should achieve. So the first key task is concerned about decomposition. So answering the question how to divide the complex task into a set of subtasks that can be easier uh, achieved by the robots. Then we have typically this set of subtasks, and we have a set of agents available for the mission. So then the next stage, the next design stage is about forming coalitions. So what agents should work together such that these subtasks can be solved in an efficient, in an optimized way. Once these coalitions are available, we have to assign the subtasks to the specific agents for the execution, and finally they are executed. And here, this execution typically uh, includes planning and controlling actions in order to complete the subtasks. So these last three tasks, they are typically highly interconnected. So task execution, the state of the task execution may interfere with reallocation or even with formation. And so this is typically executed with some interactions. What is also quite obvious is that we see a varying degree of automation for these design blocks, depending on whether humans are still involved in, for example, task composition, or it's just executed by robots and their corresponding subsystems, or whether some tasks are executed online or in an offline manner. Okay, so now I would like to go into some more detail about some specific team behaviors. What I will show in the basically rest of this webinar is 3 examples of our work here at the University of Klagenfurt, how we have achieved team behavior with a special kind of robots, in particular drones, so aerial robots, and these are very resource constrained robotic entities. So the first example is about this collision-free and efficient task planning. So how you saw the video at the introduction, and now I present some details how we can identify fast and safe constellation changes for many drones, and how can we achieve some optimization criteria like mission time and energy consumption. The second example is about route planning. So here we're interested in identifying routes for specific surveillance, persistent surveillance or monitoring applications. So where robots move in an environment, they go from waypoint to waypoint, and they should do this with minimizing the latency. So once the data is available at the base station, they need to consider the idleness, so how often or how frequent they visit specific observation points in the environment, and naturally they should also consider energy constraints of the drones. And we would like to achieve that with continuous connectivity or with intermittent connectivity. So there are various problems we can look into. And last but not least, I will briefly talk about these swarmolators, so these simple oscillator models that concurrently consider swarming and synchronization of agents. And the interesting property is that by following very simple rules and very simple data exchange, we see emerging behaviors of these aerial drones. All of these experiments have been conducted at our drone hub here at the University of Klagenfurt. You can find more information via this link. So let's talk about motion planning and motion planning in robots. So the first 2 examples are about planning this motion. Just to make clear that there are 2 key aspects of motion planning. The first one is path planning, where we are interested in kind of the trajectory from one point to another point. When it comes to route planning, we typically concerned about navigation in an environment. And here we are on a more abstract level, so we move along individual waypoints, and we are not so much interested in how to precisely move from one specific point to another point of the agent. And how to do this and how to implement planning and coordination strongly depends on how we model the environment and the robot. We can do continuous models, we can do abstract models like graphs or grids, and naturally also there are quite some differences on how we model the dynamics of the robots, whether we have very detailed physical movement, whether we are just concerned about establishing linear movements for the model. And typically we have different constraints and objectives to consider. Naturally, very important constraint is collision-free movement. We typically in spaces where we have limitations, and as I already mentioned, about the connectivity, we can either require or assume permanent connectivity among all agents, or we can consider intermittent connections between the agents. And then actually energy consumption, mission time, and so on and so forth are other important optimization criteria. And as we've already mentioned, this is a rather complex optimization problem. Okay, so let's talk about this constellation change approach. So how did we do this? As you have seen in the video, basically we start from known starting points and we want to achieve path planning to known endpoints of the drones of a specific size. And we do that to avoid collisions among each other, and also we want to reduce the transmission time and the energy consumption during this constellation change. So what we do is we follow a two-step planning approach for this coordination problem. So the key idea is that we first start with some kind of rough planning of for the individual drones. For that, we simply apply some standard model predictive control. However, the problem with this model predictive control is that there might be collisions. Okay, so when we plan individually for each robot, we might cause some collisions. So we need to take care of that and avoid or reduce the potential collisions. And we do that with potential fields. Once these initial plans have been established, then we optimize within some spatial constraints the trajectories to achieve fast transitions, to maintain collision-free movement, and also to lower the energy consumption of the movement for each drone. All right. So we implement this model-based model predictive control. So we use standard system dynamics of the robotic platform. I don't go into the details about the mathematics. What we are concerned about here are these collision constraints. So basically maintaining a minimum distance among each pair of robots all the time in order to avoid collisions of drones. So we maintain kind of safety regions around each drone, and then we can establish a quadratic program in order to solve for the accelerations for each drone, subject to specific constraints about maximum velocity, maximum accelerations, and the various cost functions H and F that are somehow that represents the constraints for the transition of each agent. So the output would then be rough plans for the drones, maintaining collision-free movement because we impose this collision constraints. So what we do and how we expanded this is we can, via this collision constraint, we can estimate whether in the next k steps the safety regions of neighboring drones would intersect, and this would be an indication of a risk for a collision. Once this is identified, we apply simple ideas from potential fields where we introduce attraction and repulsive forces. So the attractive force, what is indicated here in this figure, wants to move the agent P1 towards its end position P1, and the repulsive force then wants to push the agent away from neighboring agents like P2 here, the blue one. So we slightly adapt the plan so that we do not result in an intersection between the safety bounds indicated by this red and blue circle of the drones. When we do that, we can significantly lower the potential collisions of the drones. And then the second step is minimization of towards energy consumption and mission time, and we apply a snap minimization because this is very beneficial for these quadrotor drones within this dynamic volume constraints. So these dynamic volume constraints are based on these safety regions of these spheres. We can compute this and adapt the size of the safety regions depending on how close drones are adjacent to each other. So we have this kind of dynamic volume constraints over the mission, and we allow that the optimized trajectory can fit here within this dynamic tubes, so to say. And by doing that, we can achieve an energy efficient and fast movement of all drones in a collision-free way from the starting points to the endpoints. Okay, just a quick look at some of our results. So we have done this in simulation, and we have also implemented them as you've seen in the video. And we compared this with the standard model-based model predictive control, and in red and blue and green are two versions of our implementation. When it comes to the transition time, it's very clear that our approaches are superior to the model predictive control, which is indicated here on the top left. On the top right, you see kind of the ratio of the energy reduction. The ratio of the energy reduction of the model predictive control and our approach. So what you see here, when the density is rather low, also MPC can achieve some reasonably energy efficient solutions. When we are somewhere in the middle of the density, which corresponds here between 3 and 5 agents per square meter, we achieve the best improvements, a factor of almost 80 concerning the energy reduction. And then when it's more dense, there is quite some limited flexibility of the trajectory optimization, and energy efficiency drops. And on the bottom, you see kind of the optimization success, which is a factor on how many. So we used in simulation many. We planned for many different passes in simulation, and success rate, optimization success is the ratio of how many of them have been implemented in a collision-free, how many of them were feasible, so that all agents achieved their target points. And you see, when the density is below a certain threshold, basically all different variations are successful, so they achieve, and then there's a slight decrease when the density is higher. And finally, the computation time, it increases with the number of agents per square meter. Our approach requires slightly more computation time, but it's in the same order as our baseline. Okay? So that was the simple case. Then we expanded this towards environments where we have obstacles in the environment. Right? So we can either deploy obstacles kind of in a random fashion, or another interesting case study was that we establish the drones in a way so that they need to fly through a window from the start points to the end points, and we can nicely vary the size of the window and measure different effects. We also used a very similar path planning approach, the two-step path planning approach. However, here we replaced the first initial planner. We used a discrete multipath planning approach. So basically, we used an enhanced version of conflict-based search where we discretized the environment and allow agents to move to neighboring grid cells, and depending on the path and the spatial constraints, different discrete paths emerge. And what you see on the bottom is one example of such a discrete plan. And then we also apply snap-based optimization as in the previous example, and achieve kind of energy efficient and fast constellation changes in environments where there are where there are obstacles. A specific problem in these environments with this discrete planning approach is that waiting events may occur. So that means that at a specific point of time during the planning at some position, an agent has to wait because none of the neighboring cells is free. They are blocked either by obstacles or by other drones. And these waiting events are critical because they impede smooth and energy efficient trajectory. So agents would need to stop, hover, and then accelerate again, and this is not energy efficient. And we would like to avoid this. And we did this by basically introducing much more movement actions within this three-dimensional grid of the discrete environment, and by doing that, we were able to significantly lower this waiting events for our plans. Okay, I don't go about the details of the simulation results here in this presentation. I want to continue with the second example now. Okay, so the first example was how can we plan paths for multiple agents such that they move from point A to point B, or from a specific constellation to an end constellation. Now we talk about cooperative route planning for persistent surveillance. Right? Persistent surveillance, we have a set of sensing points the agent should visit. They sense the environment, and this captured data should eventually delivered to the base station. Right? And we can distinguish here about connectivity about two main systems. In the first system, we want to maintain connectivity throughout the entire mission, so that the agents are connected for the entire time. And in the second one, we allow intermittent connectivity. All right? So yeah, these are some examples why this route planning is so important for monitoring, for persistent monitoring. This is relevant for search and rescue observations, for inspection tasks, for uh, firefighting tasks, and so on and so forth. We typically operate with in outdoor environments with wireless connected drones. So an important parameter to keep the network connected is to maintain kind of the maximum distance between the drones, so that we maintain at least one pass over multiple drones towards the base station. Right? And so we need to coordinate the movement of the robots. What we have done here is we framed this also as a discrete planning approach, where we want to minimize the worst idleness. The worst idleness is what's the maximum times between two consecutive visits on a particular sensing location. And the sensing locations are here depicted by these gray cells. Right? And we want to achieve that, and we want to maintain this movement in the environment such that there's always a path either directly to the base station or over some relay drones, so that the network is always connected. And a particular challenge is that since the energy is limited of these drones, we have to make sure that the agents periodically are able to move back to the base station to recharge the batteries and then start flying again. So this is a hard problem. What we did is we investigated different motion planning heuristics, depending on how far we looked into the future versus we just looked at some short periods of time and planned for the short period of time, or we went to look for the entire mission into the future. That is then referred to as full horizon plan. And then there's naturally also a distinction whether we look at heuristics for individual drones or particularly where the drones prepared cooperative planning, so they informed others about their movement and then they responded, they reacted appropriately. Because when you do not support cooperation here, maintaining the connectivity is difficult to achieve. Okay? So for this planning, we adopted simple goal-based heuristics. And so basically each cell in the environment comes with a cost. Okay? And this cost depends on a specific drone and is responsible for a specific cell. And the cost is composed by three parameters. So the idleness, so how long that the cell has not been visited. What is the distance to the cell, between the drone and the cell, and what is the minimum distance to all the other drones in the environment. We have then two weights, W0, W1, which we can determine with some experiments up front. Okay, so I do not show all the animations here, but you can simply follow this goal-based approach. But what is also challenging here is that this goal-based approach, since there is no interaction between the drones, maintaining this connectivity is difficult. So because in order to maintain connectivity, you have to make sure that the maximum distance between drones is maintained. So and we did this by introducing so-called safe paths for drones, so that they are able, at each point in time, they are able to return back to the base station in order to recharge their batteries when the battery is about to get depleted. And so the consequence of the safe path is that since we want to maintain connectivity, also the neighboring drones also need to move towards the base station to keep the network connected. Okay, and then the cooperative planning approaches, they, as I said before, they exchange information about the intended movements. We do this by applying some graph matching approach where we inform the others about how to move, how one moves towards the next cell, and this helps to or this guarantees that the maximum distance between drones is not violated. And then there are also full horizon planning approaches where we separate the drones into leader drones and intermediate drones, and the leader drones is responsible for moving towards the sensing locations, and the remaining drones make sure that the network is always connected. Depending on the number of drones and the environment, we can even partition the entire monitoring region into specific areas, and for each area, a team is then responsible for fulfilling the observation, the persistent monitoring task. Okay, I don't go into the details about the assessment here as well. I just want to mention that we can expand this planning approach about persistent surveillance also to systems where we allow intermittent connectivity. So for some periods of time, the drones may move independently of each other along predefined routes. However, they have to make sure that at some point of time they meet at some kind of neighboring locations, and then data is communicated, or the captured data from one drone is communicated to another drone. And so in this kind of piggyback method, eventually the data is delivered to the base station. Right? So the key question here in this store and forward approach is who should meet when and where. And this depends obviously on the environment, but also on the optimization criteria. However, it can be simply shown that this problem is a difficult one, so it's an NP-hard problem. And what we've done is we investigated different robot scheduling algorithms for known or for given tools. A tool is kind of the route of an individual agent here along a specific part of the environment. And this robot scheduling algorithm are concerned about in what direction the robot should move, in a clockwise direction or in a counterclockwise direction, where should be the meeting points, and when should they wait, and when should they exchange data. So this is depicted here on this graph. So on the left-hand side, you see these individual tools indicated by the circles, and these dots represent the meeting points, and you can model this as a graph, as a data transfer graph, and then you can identify the schedules where, say, for the longest circle, so this one, you assume that the drone moves without any waiting time, and then you schedule correspondingly the movement along the other routes, and to make sure that the latency is minimized, meaning that once the drone has visited a specific location, sending location, how long it takes until this data is available at the base station. And there are different instances of this problem. So we can, on the one hand, we can try to minimize the latency for a bounded idleness. So meaning that the idleness means what is the maximum time a specific sensor location has been visited. Right? And then there are different options on how to do that. And the second approach is that we minimize the idleness for given tools and latency constraints. So this is even more complex. Right? And as I said before, I don't go into the details of how we did that. The point here is really that it's many of these instances are very hard problems. Last but not least, I want to briefly talk about the third example. So this is about swarming and synchronization. And in this example, I want to briefly explain how an emergent self-organizing team behavior can be achieved by very simple mathematical models for the behavior and by simple coupling of these models, considering synchronization or phase displacement and spatial displacement, and how to do that. Okay, so when it comes to this kind of self-organization principle, I think we know that two key self-organization principles are related to synchronization. So here we want to coordinate the time domain. Typically, this is done by adjusting the phase of the local clocks at each robot. So what you see on this graph is on the left, you see different colors indicating different phases of the local clocks of the agents. And then when it's about synchronization, we want to make sure that all agents agree on the same phase. So basically, they blink at the same frequency, or they have the clock running at the same rate and at the same phase. When it comes to swarming, we are concerned about coordination, the movement of the or the location of the robot. So here we coordinate in the space domain. So what is here are positions of individual agents, and when we talk about swarming, we want to impose some simple rules about the spatial position, the locations of the drum, like in this linear pattern. A swarmulator is now a unified model where we couple the robot's phase, the temporal domain or the time domain, and the space domain. Okay, and we do this with a simple model, with a simple oscillator model, and depending on the parameters, we see different space-time patterns, so synchronization and swarm behaviors emerge from these entities. Right? So what you see here is this kind of mathematical model of this swarmulator. Right? So this swarmulator model contains two key ingredients. The first one defines this phase-dependent movement. Okay, so here we have the first derivative of the position of an agent, basically the velocity, and the velocity is defined by kind of the attraction, so how close, based on, and the attraction is measured by how close the agents are, and the repulsion. So there are these two forces, and the attraction is then multiplied with this factor. And what we see here, there's a parameter J which influences the strength of the attraction. The second ingredient of this formulator model is the location-dependent synchronization. So here we have the change in the phase, which is also dependent on the attraction. Here are what's the phase difference between the agents and the specific factor. Okay? And we multiply this also with another parameter K. Okay? So we have these simple models. They are jointly connected. So we have the phase and the distance, the phase, the distance in both models of the input, and this influenced then the time derivative of the position and the time derivative of the phase. And what you can see here is that different behaviors emerge. What you see here is this taken from this website, the complexity explorables. And here you can find different self-organizing behaviors, self-organizing systems. So what you see here is a specific pattern that emerges based on a specific value of the synchronization strength K and the attraction strength J. Okay, and then you can achieve these different behaviors. And depending on the parameters, you see different behaviors. For example, a static sync. So here you have very little movement. However, all of these agents follow the same phase. So they achieve synchronicity. You can also achieve static asynchronous behavior, where you have similar movement patterns. However, you make sure that all nodes, or the nodes, are not in sync. Right? This is sometimes an intended case, for example, to establish collision-free synchronization. And you, by playing around with these different patterns, you can achieve static phase waves, so where you have this ring, and basically the ring is ordered based on the phase, or you can also achieve a pattern where you have subgroups, and so on and so forth. So when it comes to the implementation of this simple mathematical model, we need to adapt the simulator model for the using robotics, because there are some fundamental assumptions, so that all nodes are communicated with all have identical behaviors, there's no delay in it, there are no movement constraints, there's no speed limitations, collision avoidance is not handled, and so on and so forth. And colleagues here in Klagenfurt have implemented this and investigated this in robotic platforms. And what you see here is a flight of these small drones, the crazy flies. And in these crazy flies, we implemented the swarmulator model. So what you see here is the color represents the phase, and the first one is kind of the static sync model, where the 8 drones agree to the same phase. They do not basically move. Then we change the parameter. We see this async model. By applying different parameters, we see this kind of ring approach where the nodes themselves arrange. So this is not, it's important to mention, the movement is simply based on these coupled swarmulator models. Right? So what you see here is then that these drones arrange to the specific formation. It's a ring, and their neighboring faces are adjacent to each other. Okay, so I think time is running out. I want to wrap up. So what we've discussed in this webinar is that I introduced this coordination problem, and the complexity of multi-robot systems is steadily increasing. In order to solve this problem, we typically take advantage from an interdisciplinary approach. And this is also what we have done here in Klagenfurt. So we combined projects from control theory with nature-inspired terms. We work together with communication experts in order to solve these issues for multi-robot environments. In our methodological approach, we investigated kind of many of the problems, not only in simulation, but also we deployed them on real multi-robot systems. So this is challenging and requires a lot of engineering work, but on the other hand, provides also interesting feedback from the real challenges of the engineering towards some basic research questions. And also important when it comes with robotic research, there are many non-technical issues about safety, legal, ethical, regulatory aspects that need to be considered as well. And the key lesson is, in order to achieve results, you need to have endurance. Perseverance is an important part of the game. Okay, so what we have shown is we have shown route and path planning approaches and this formulator model, and the coordination, I think, should be well understood that this is challenging and is fundamental for many multi-robot systems applications. But we need to look for efficient heuristics to considering performance bounds. We also have to rely on various simplifying assumptions, and there are many open research questions available. So all of this research has been conducted at our drop hall here at Klagenfurt. And last but not least, I would also like to acknowledge contributions from my research group and from the colleagues here at Klagenfurt University. So thank you very much, and I'm open to your questions.